Oh my god, that's it. Yeah. To here.
Hi, everybody. Okay, hey everybody. So there is a remnants of a typhoon that are climbing into Arizona right now. I have some graduate students out there trying to use the telescopes and failing. And this weekend the weather is so bad that we've decided to reschedule our trip to Arizona 3 weeks in the future. So it's going to be in 3 weeks. The good news, the bad news is that you won't get your data for your research projects for another 3 weeks. The good news is that we will be on actually a larger telescope. There's a larger telescope on the site, 1.8 meter telescope compared to what we were going to use, which is about 0.9. So we have factor 2 in diameter, which is factor 4 in area. So it's a much more powerful telescope. And that's the one we'll be using. And the other bad news is that it will be a quarter moon, so there'll be a little bit more moonlight, which will make it a little bit harder to do some of the faint work. So the it'll be a little bit harder for that reason. But the larger aperture is helpful. Now we're also, because of this, we are going to have discussion tomorrow. So we will have discussion, we are here, so we will have discussion tomorrow. And also we're going to move the time for the presentations back. So we haven't figured out exactly when yet. So hang tight, the research project is just getting extended a little bit because of this. Now the weather could be bad in 3 weeks, but we thought given the cost of changing it, it was worth doing. So we may still have bad weather in 3 weeks, but that's okay. The odds of us getting data are higher now than they were otherwise. Okay. Anybody have any questions about that? Yeah. Lab for next week?
I would suggest you check the lab syllabus. Do we have lab next week?
No.
There we go. So the lab schedules, because of this change, just to clarify, the lab schedules will not change at all. Labs are still all the same schedule. The new date will not affect any labs. So there'll be no changes at all for labs.
Yeah, the change is that we will have discussion tomorrow at our regularly scheduled times. I don't know if you guys all processed that we weren't going to have discussion tomorrow, but we weren't. Now we are. We processed that unprocessed. Okay, any other questions? So we will be, as Dr. Muir said, we're gonna rearrange the lecture schedule a little bit to move the class presentation part of our research project back a little bit. We'll probably move the deadline for the written papers that you're writing back a little bit. We have a little bit of juggling to do. We just made this decision last night, so we haven't quite fully figured out all the consequences yet. But we have a lot of time left in the semester, so it won't be an issue. And hopefully we'll get better weather. There's a problem with trying to collect astronomy data in the rain, which is that you can't. Because you can't see through the clouds and you can't open the telescope building because then you get rain on the telescope mirror, which is not so good. We could do the geology parts in the rain, but it's not that much fun. So we're going to push it back a couple weeks and hope for better weather. All right. So, where were we when we left off on Tuesday? We were talking about the early Earth. And that's what I want to pick up on today. So I want to talk a little bit...
Can you change the lights
I did.
The one back here is flashing.
Should we just turn off more lights?
Yeah. Do that. How about that? You guys got fun lights? Alright, everybody's going to sleep? Okay. Do it like that. So, what I want to talk about today is a little bit more about geochronology, about telling Earth time. I want to talk about what we know about the early Earth. And I want to talk about plate tectonics, which is a framework which helps us understand how the solid part of the Earth works today. We'll talk a little bit about the origin of the atmosphere, the origin of the oceans, and the origin of the continents. This is a painting imagining what the Earth may have looked like during the Hadean eon. And the Hadean eon is sort of an informal slice of geologic time
reflecting the first half billion or 500 million years of Earth history. So everything from 4.568 billion years up to about 4 billion years ago. About which we know very little, but we're able to reconstruct some of the events of the very early Earth, and that's one of the things I want to talk about today. So what are some of the things you noticed here? Yeah?
There's a new moon.
Okay. That's not like just a new moon, like a new moon in the sky like we see once a month, but like a new moon, like it just got formed. Yeah. And we can tell it's new because it's still very hot, right? So that's, and what else can you see about the moon? It looks abnormally large. Yeah, so we do know, and we talked about this a little bit, that when the moon first formed, there's pretty good evidence that it was closer to the Earth, and it's been very slowly moving away from the Earth. And so this diagram shows that. What else do we see? Yeah, what was that? There's no blue sky. Yeah, so the sky looks different. That's a good point. I hadn't really thought about that. Maybe it's just a nice sunset. The sun's actually pretty low in the sky. There's a lot of meteors in the sky for typical Thursday afternoon. Right, you can see 4 right now, and that's reflecting actually some a part of the history of our solar system, which is referred to as the late heavy bombardment, where there is evidence that there was a lot of debris in the solar system running into planets, probably Earth, and certainly there's evidence that they were running into the moon. There's quite a lot of molten rock at the surface too. So some of these, are things that we think we know about the early Earth, and so this is a reasonably realistic picture of what the Earth might have looked like on a Thursday evening in the Hadean. Okay, so returning to this, I told you guys that I was going to ask you a question at the beginning of class today, and I haven't forgotten. I gave you the half-lives for the 2 radioactive isotopes of uranium that decay to stable isotopes of lead. One of them with a half-life of 4.468 billion years, and the other with a half-life of about 703 million years, yeah, 0.7 billion years. And then I said, okay, we can take those half-lives and we can make some measurements of uranium and lead concentrations in an ancient zircon. And so as I mentioned, this is a zircon that was collected from sandstone in Australia. And the sandstone itself was probably a beach about 3 billion years ago. Right? So the sandstone has been reasonably well dated to about 3 billion years old. Okay? But it contains grains of sand which came from the erosion of rocks that were much, much older. And when you start poking through those rocks and looking for zircons in there, you find a lot of zircons that are older than 4 billion years, which is a really unusual thing to find on Earth. And the oldest one that's ever been reported was reported by Wild et al. In a paper that came out in 2001 in Nature. I'll show you in a second. Simon Wild was a graduate student at the time, so this was his PhD thesis work. And it made a huge splash, right? Because he had successfully dated the oldest material ever found on Earth that wasn't a meteorite, right? The oldest material ever born and raised on Earth that has ever been found, right? Here's the raw data from their paper. So we got a 206 lead, 238 uranium ratio of just a little bit less than 1, and a 207 lead, 235 uranium ratio of about 75. And you can see that there's a plus or minus there, and that plus or minus represents the analytical uncertainty, right? Because we're measuring on a mass spectrometer these isotope ratios, and there's a little bit of uncertainty which eventually will propagate into a bit of uncertainty in the age. But the question I left you with on Tuesday as class was coming to a close was how old is this zircon? Anybody come up with an answer? Sorry, somebody said something? No? Anybody have an answer? All right, well think about it. I'm going to take a nap. I'm tired, it's been a long week. I'll just take a nap. And then I'll wake up, and you guys will have an answer for me. Nobody has an answer for me? Nobody wants to volunteer any information whatsoever? Okay. All right. Let's see if we can walk through this. All right, so we're looking at, okay.
Andy, there's a hand down there.
Oh, wait, where? Ah, yes. 8.712 billion? Okay, we don't like that answer. That answer's been retracted. And why did you retract it? It's older than the meteorites? Yeah, that's actually a good way to check your thinking. Anytime I do a calculation like this, I think about whether my answer looks reasonable, and if it doesn't, I redo the calculation, and if it does, I redo the calculation, because I make mistakes on stuff like this all the time, right? So I like to check my logic. Yeah, so 8 billion years old doesn't make a lot of sense. That's too old. It's older than the solar system. Anybody else? So what we're looking at here is a ratio of a daughter isotope to a parent isotope. Okay, and maybe one of the things that I haven't told you about zircons which will help is that when a zircon forms, it's got a fair bit of uranium in it, okay, but it has no lead. Zircons are magic like this. When they crystallize from a melt, their crystal structure doesn't have any space for lead to fit in, so they basically exclude lead. So they start with no lead. And then the only lead that's in a zircon after a billion years or so is the lead that came from radioactive decay of uranium. Okay, does that help at all? All right. So what can we say about, let's ignore this one for a second. Let's just look at the top one, 206 lead to 238 uranium. The ratio is not quite 1, almost 1. What is that telling us? Okay, all right, I heard something good here. It's very close to the age of 1 half-life, right? And so for this isotope system, for 238 uranium decaying to lead 206, think about here is you start with no lead after 1 half-life, okay? Exactly half of the uranium is gone and has become lead. And so the ratio of 206 lead to 238 uranium will be exactly 1, right? And the ratio in the sample that we're looking at here is just a little bit less than 1, which suggests that we haven't quite got to 1 half-life, but we're almost there. Okay, in contrast, the ratio of 207 lead to 235 uranium is not just greater than 1, but it's quite a lot greater than 1. It's like 75. And so that suggests that this has gone through many half-lives. Now how is that possible? How can it be only 1 half-life for the 206 lead, but many half-lives for the 207 lead? Yeah? Yeah, it's a much shorter half-life. Okay, so this is one of the critical things about using zircons for geochronology, and one of the really powerful things about uranium lead is that there are 2 independent clocks, one that runs really fast and one that runs really slow, but they both should give you the same time, right? And if they don't, they're telling you that something's wrong with your clock and you can't trust it, right? In this case, as I'll show you in a second, the clocks do agree. Okay, so bear with me here. This is a plot called Concordia curve. And back to here, how old? We're going to say that the age of this zircon is a little bit less than 4.46 billion years, right? That half-life of the 206 lead system. Okay, so Concordia curve. And what we're looking at here is the ratio of 207 lead, which is the daughter of 235 uranium, on this axis, increasing in that direction. And the ratio of 206 lead to 238 uranium increasing in this direction. So daughter to parent, daughter to parent. Okay? pointer here, so this is going to be a little tricky. But let's think about these numbers. So we got about 75 and about 1. Okay? Anytime the two clocks, the 235 uranium clock and the 238 uranium clock, are in agreement, telling the same time, then those numbers should plot somewhere along that line. Okay? Oh, thank you. Okay, I won't point it in my eyes then. Okay, so what are the numbers we have here? Well, okay, 206, 238 uranium is about 1. Right, not quite 1, so over here. And the 207 to 235 ratio was about 75, so right here. So it looks like it's plotting on the Concordia line, meaning both of the ages, both of the clocks are in agreement, and the age is just a little bit less than 4.5 billion years. So that's good. This tells us this is a good age. Right? Yeah?
So the Concordia curve just mean like, just making sure that both of the geological clocks are in sync?
The Concordia curve means that both of the geological clocks are in sync. That's right. Sometimes you'll find samples that don't plot on the Concordia curve, and what it means is that something has happened. In some way that sample has been disturbed. Okay? So when both of the clocks are in agreement, it tells us that the zircon crystallized and it's been sitting there accumulating lead over all of geologic time, and when we measure the two isotope ratios, we get the same age. It's good, we can be confident in that number. Okay? So we would call that a concordant zircon. And so the farther along this curve a zircon plots, the older it is. Right? So a newborn baby zircon doesn't have any lead in it at all. It plots there, right? Because it's born without any lead. It hasn't had time to accumulate any lead. The 206-238 ratio is 0. The 207-235 ratio is 0. Right? After 20 million years, right, we've gone through several, or sorry, after 3 billion years, we've gone through several half-lives of 207, so that ratio is, or sorry, several half-lives of 235 uranium. That ratio is going to be large. We haven't yet got to 1 half-life of 238 uranium, so we're not quite at 1 for the daughter-parent ratio, so we're going to be up here somewhere. And then as we progress, we can move along that line. Okay, so here is the figure from that paper by Wild et al. that I mentioned. Okay, 206, 235 on this axis, 207, 235 on that axis. This is the Concordia curve. All right, and when they measure on that SHRIMP, the scanning high-resolution ion microprobe, the instrument that they use to make these measurements, they find that many of the zircons don't fall on the Concordia line, but a couple of them do, and they plot at a location on the line equivalent to an age of 4.404 billion years. This is the oldest sample of Earth materials that's ever been measured. It was measured back, it was published in 2001, and nobody's managed to beat that yet. So this is the oldest thing that we have from Earth. Okay? Interesting thing here is that a lot of these zircons don't plot on the Concordia line, right? They plot actually on a line with a pretty clear trend like that, but it's off of Concordia. Yeah? It was disturbed, exactly what I'm looking for here. Okay, so imagine this. Let's imagine you've got like this crystal lattice, all of these atoms linked together, bonded together. The zircon has got zirconium, it's got silicon, it's got oxygen, and it's got uranium sitting in some of the sites in that crystal lattice. Uranium undergoes radioactive decay. It's ejecting alpha particles one by one to lose enough mass to become lead. And then that site in the crystal lattice is actually really damaged, and that lead is kind of rattling around in that site. If you then heat the zircon or leach it or something like that, generally involves heating, you can actually lose some of the lead from the zircon crystal. And when that happens, if you're losing lead, you're going to move from this wherever you are on the Concordia curve back towards the origin, back towards 0. If you drive out all of the lead, you end up all the way back at 0, and basically you reset the clock. right? And this Discordia line has an intercept up here at 4.404 billion years, and it's got another intercept down here at about half of a billion years, 500 million years right there. And the way that the geochronologists interpret data like this is that you had a bunch of zircons that crystallized 4.404 billion years ago, and then about a half a billion years ago, they were involved in some kind of tectonic event that heated them and caused them to start losing lead. Some of them lost almost all of their lead and were pushed almost all the way back to zero. Some of them didn't lose any lead at all. And then over time, they've all continued to evolve on that line. Right? So that's a little technical. What I really want you to get away from this is that the best preserved ones give us an age of 4.404 billion years. That's the oldest thing that's ever been recovered from Earth. And second order effect is that they tell a consistent story of having been disturbed like a half a billion years ago. Probably some collision involving the continent of Australia where these rocks have been living for the last 4 billion years. All right? You guys happy with that? You're going to see Concordia again. We'll probably have a homework assignment that we'll assign tonight. What do you think? Yeah, we put together a homework assignment, first geology homework assignment. We'll probably assign it tonight and have it due a week from today. And you might see some Concordia stuff on there. See some other radioactive decay stuff there too. Anybody have any questions about this? Okay. Yeah.
So the really old ones, are they fragile because of all the radiation?
Physically fragile. I think that the uranium is present in such small concentrations that it doesn't do significant damage to the mineral except for the crystallographic sites where the uranium used to sit, and those are susceptible to leaching loss. Basically, the mineral gets heated up and the lead diffuses easily out of it. And one of the things that I didn't really make clear is that a lot of these data points are different parts of the same zircon crystal, right? So the outer part of the zircon crystal might plot down here, whereas the core of the zircon might plot up there, right? So you get better preservation of the inside of the zircon than the outside. And that's only possible because you have this scanning high-resolution ion microprobe, where in one crystal that's less than a millimeter long, you can measure the age of a bunch of different spots and come up with things like that. Right? So really cool stuff that you can do to make inferences about what was going on the Earth. Okay. Important point about what it is that we're actually dating. So when we say we can determine the age of a rock, what does that really mean? Well, what it means is that we're determining the amount of time that's passed since the mineral or the rock became a closed system, since it basically stopped communicating with its surroundings. Okay, so if you're, a dead mastodon, right? The time which you stopped communicating with your environments was when you stopped eating food and breathing out CO2, right? Stopped exchanging carbon with your environment. And so that would be the point at which the radiocarbon clock starts recording time. For minerals and uranium and lead and things like that, generally what you're recording is the time since the mineral formed from a magma, since it crystallized out of a magma and became a solid. Sometimes, for some isotope systems, particularly for things like argon, which is a gas, the mineral can continue exchanging or losing argon to the magma while the mineral is solid, but the rock is still very, very hot, right? In some cases, the clock actually starts when you get below a certain temperature, 500 degrees C, 700 degrees C, something like that. Rocks crystallize temperatures on the order of 1,000 degrees C. And so we call that point the closure temperature. The closure temperature is basically the point at which loss of the daughter by diffusion becomes so slow that basically the mineral starts recording time. Right? So generally what we're dating are cooling or crystallization of minerals. And when we look at Earth rocks are crystallizing all the time, and so we can get a whole span of ages. Like this, for example, is a sample of diorite, which is an intrusive igneous rock. This makes up the continental crust on the island of Puerto Rico, where I collected it. It's a granitic type rock, typical of what the continental crust looks like. And it's only about 50 million years old, which is really young relative to, say, the crust that we have around the Boston area, which is more than 10 times older than this, right? Just by looking at the rock, you wouldn't be able to have any idea how old it is. It's only because we have this information recorded by radioactive isotopes that we can determine ages. Yeah?
My understanding is that chondriaceous meteorites are not differentiated as they were for this kind of what resets the clock in this meteorites?
Okay, so what resets the clock in chondrites is basically when, it's again, when they stop communicating with their environment. So when they accrete and become a rock that can hold on to the lead, rather than exchanging lead with all of the other bits and particles in that nebula, that's when the clock starts.
Unlike the zircon, they're bringing indigenous lead in.
They are bringing indigenous lead. This is a very important point that we're going to get to in a second. Okay, so if you remember nothing else from this lecture, zircons are really special. Okay? So there's a James Bond movie about how diamonds are forever. Right? Diamonds are not forever. Diamonds are actually unstable. If you give me your diamond earrings and I put them in the furnace in the basement at 1,000 degrees, they're going to recrystallize it and carve it into graphite. Because diamonds are not stable at the Earth's surface. They're very, very slow to recrystallize into graphite, but they're not actually all that stable. Zircons, on the other hand, are unbelievably stable. And this is what makes them such magical tools for geochronology. All right? They stick around forever. Right? The oldest minerals we find on Earth are zircons. And you can beat them up, you can heat them, you can do all kinds of stuff to them, and they just stick around. And in fact, when we're working with zircons in the laboratory, the only way we can get them dissolved is we put them in what we call a bomb, which is a Teflon capsule that goes inside of a steel jacket, and we fill it with hydrofluoric acid, right? And then we put it in the oven at 200 degrees C, which is way above the atmospheric pressure boiling point of that acid. And we leave it in there for like 3 weeks. And then after that point, we take it out, and if we're lucky, the zircon is dissolved, right? Very, very hard to break those bonds in a zircon crystal. So zircons are really, really stable and really, really nice tools. And when they crystallize, they don't have any lead in them, which is great, because it simplifies the assumptions that you have to make. As Dr. Cartmill mentioned, when you make a chondrite meteorite, or when you make virtually any other kind of rock, it's got some lead in it to begin with, which is a complication that we'll get into in a second here. Okay, so this is Claire Patterson. Claire Patterson is one of the real heroes of geochemistry. He went to graduate school at the University of Chicago in the late 1940s after World War II. During World War II, he was working at Oak Ridge National Lab in Tennessee, where he was part of the Manhattan Project. And one of the things that they were doing in the Manhattan Project is they were inventing mass spectrometers and learning about the chemistry of things like uranium. Right? So then he went off to graduate school and he said, okay, you know, working on this bomb project was great and everything like that, but what I really want to do is I really want to use my knowledge to try to understand something about natural science. And so the project that he was assigned as a graduate student was to try to figure out the age of the Earth. Right? It's a pretty ambitious project for a graduate student, but he had the tools to do this, and his advisor recognized that if you took the right materials, meteorites in particular, and you measured the isotopes of lead and the isotopes of uranium in them, and you made this kind of calculations we've been talking about, you ought to be able to come up with an age of the Earth. So he started graduate school in the late 1940s, and I think the first paper that came out, Patterson et al., that gave an age of the Earth, of the solar system, was like 1956. So it took a long, long time. He finished his PhD. He went on to become a professor at Caltech in Pasadena, California. And that's actually the point when he finally figured out how to do this. Patterson's part of the project was the lead part. His lab partner got the uranium part. So his lab partner was measuring uranium. Patterson was measuring lead. And what he found was that when he would measure, he would take these meteorite samples, he would isolate the lead from the meteorites, and he would measure the amount of lead and the isotopic composition of the lead. He got really, really inconsistent results, and he got way, way more lead than he was anticipating getting based on the amount of uranium and the age. And so he figured something is wrong here. And what he eventually came to realize was that the laboratory at the University of Chicago, where he was working, was horribly contaminated with lead. All right? And then what he began to realize that not only was the laboratory at the University of Chicago horribly contaminated with lead, everything in our environment is horribly contaminated with lead. Okay? And the only way that you can get away from that is by going deep, deep in polar ice caps, right? When you get into snow that was deposited before the Industrial Revolution, or if you go to like the bottom of the Pacific Ocean where you have water that's been out of contact with the atmosphere for like 1,000 years, right? The rest of our environment is really, really lead contaminated. And Patterson recognized that this was potentially a huge problem because lead, particularly when children are exposed to it, causes all kinds of really, really terrible cognitive impairments and health problems. And he became really the first person to try to do something about this, while he was simultaneously trying to figure out the age of the Earth, right? So this work that he started as a graduate student set him down two paths. One, where he ended up doing battle with the automotive industry and with oil companies who added tetraethyl lead to gasoline. You guys have no recollection of this, but when I was a kid, you went to the gas station, you could buy either leaded gas or unleaded gas, depending on what kind of car you drove. And the reason leaded gas was around was because if you added a bunch of this compound tetraethyl lead to the gasoline, it improved the way that the gasoline combusted in the inside of the engine. It reduced knock-in, pre-combustion of the gasoline. And so that was great. The problem is that lead would come shooting out of your tailpipe, and it was contaminating everything with lead. And Patterson recognized that this was a problem, and he took on industry, and he made a lot of enemies this way. By the way, there is a really great series that was produced about 5 years ago now by Neil deGrasse Tyson. And it aired on Fox, and it's available on YouTube and Hulu and various other platforms. I'll leave it to you guys to figure out how to watch it and how much you want to pay for it. But if you want to get a really interesting story about Claire Patterson, there was a whole episode. It was episode 7. It was called "The Clean Room." That was about Patterson's story, both about determining the age of the Earth and also the environmental work that he did associated with lead. So what does the clean room represent? Well, a clean room is a lab that you build specifically to exclude lead contamination. When I got to graduate school at Cornell in the mid-1990s, one of the first things that I was assigned was measuring the lead isotope composition of volcanic rocks from the Andes. And we were using that to figure out details about the ways that these rocks were formed in the crust and try to determine about their ages and so on. In order to do that, in order to isolate and measure the lead without contaminating it, you had to go up to the 4th floor of the geology building, enter a small room that was positively pressured so no outside air could come in, take off your shoes, gown up, put something over your head, put gloves on, walk into a clean lab where we did most of the isotope chemistry for our lab. But to do lead, you had to go into another room, which was positively pressurized and further isolated from the rest of the lab. That was like the most clean place in the entire state of New York, probably. And you had to like not sneeze while you were in there. And if you were a smoker, if you were a cigarette smoker, you weren't allowed to work in the lead lab because cigarettes actually have a lot of lead in them. And if you are a cigarette smoker and you breathe on your sample, you get lead contamination on your sample. So if you're a smoker, you might want to think about that. It's kind of gross, actually. And so that was a clean lab. That was a lead-specific lab. And what Patterson's big breakthrough was when he got to Caltech was he recognized that he needed to build essentially the first clean lab to exclude lead. And he was successful in doing that. And he eventually published this diagram. Okay, so what this is it's different than the Concordia diagram, because Concordia only works if you start with something that doesn't have any lead in it. And what Patterson was measuring were meteorites. So these are iron meteorites. I showed you some iron meteorites in class the other day. Most of the rest of these are chondrite meteorites. They all have various names here. And then the other thing that's on there is modern sediment. We'll get to that in a second. That's sediment from the bottom of the Pacific Ocean. Okay, and so the idea with an isochron diagram, which is what this is, anybody have any idea, if you're a Greek scholar, what isochron means? Yeah? Dig a little deeper into our Greek words here. So what's iso?
Equal?
Yeah. Yeah. So what's chron?
Time?
Equal time. Yeah. So basically the idea is an isochron is a line of equal time. Right? And so rocks, meteorites, materials that plot all on a line on one of these isochron diagrams are the same age. And the age can be inferred based on the slope of the line. Okay, so this is how it works. All right. On the x-axis we have 206 lead. 206 lead is produced by what? Yeah, decay of uranium-238. And that's divided by the amount of 204 lead. We haven't talked about 204 lead. 204 lead is like garden variety lead, right? It's just like, just lead. It's not produced, it's produced in stars. It's not produced by decay of uranium. It's not radioactive. It's not produced by anything else. It just sits there. So this is, you can think of this as like your normal background lead, right? The lead that was there to begin with. The 206 lead is produced by radioactive decay of 238 uranium, right? So the more uranium you have and the older your sample is, the farther over on this line it's going to plot. Okay, this one is 207 lead versus 204 lead. So 207 lead is produced by decay of 235 uranium. So same story there. Okay, and 204 lead is again just stable lead. And so again, the older your sample is and the more uranium 235 it has, the higher up on that line you're going to plot. Okay, so when you look at an isochron diagram like this, if I just took a random collection of rocks from the Earth and measured their isotope ratios like that, and plotted them on this diagram, it would just be a shotgun scatter. Okay? But if the rocks start off with the same initial lead, doesn't have to be the same lead concentration, but it has to be the same isotope ratio of initial lead, right? The same lead source. And in this case, we're talking about the lead that was present in that nebula from which our solar system formed. And then over time, the rocks accumulate 206 and 207 lead, depending on how much uranium they have. If they have a lot of uranium, they're going to end up way over here. If they have very little uranium, they're going to end up way over here. The iron meteorites have hardly any uranium in them, so they plot down here. Chondrites typically have more, so they plot up there. If these materials all start off as from the same material, from the same stuff, and they're the same age. I should say if and only if the rocks all start off with the same initial lead composition and they're the same age, they will plot on an isochron. Otherwise, shotgun scatter. Okay? So Patterson did this. He got his clean lab going. He managed to exclude all contaminant lead from the environment, which was really hard. Measured a bunch of meteorites and found that they all plotted on a line. Okay? The slope of that line, and I could demonstrate this to you if we went through all of the math involved in an isochron, but I don't really think that's necessary. Take my word for it. The slope of that line gives you the age that all of these materials have in common. Okay, and on this diagram, actually the slope gets less steep as they get older. The slope that he gets from the meteorites is 4.55 billion years. Okay, so this was the first time that anyone had ever come up with an age of the solar system. Okay, again, based on meteorites. And here's the trick. He took a sample of sediment from the bottom of the Pacific Ocean. And generally, if you go out into the middle of the Pacific Ocean, well away from any river sources or anything like that, the sediment that's out there has lead in it that comes from dissolved lead in the ocean that accumulates in sediment on the seafloor, and windblown sediment that comes from the continents. So that sediment is basically mixing earth lead really effectively. So you can think of this modern sediment as being basically average lead from the continents. And when you do that, you find that it plots right on that isochron diagram with all of the meteorites. So the fact that Earth's lead plots on the diagram, on the isochron diagram, indicates that Earth came from the same source as all of the meteorites and is the same age as the meteorites. Okay, so when we talked about like the age of those calcium aluminum inclusions and the chondrites, and I said that's the age of the Earth, and it's 4.568 billion years, that's the initial crystallization of our solar system. This is the evidence that really ties Earth to those meteorites. This is how we know that meteorites represent the stuff that Earth formed from. Okay? So this is a really important, I think, contribution that Claire Patterson made as a scientist. Okay? Any questions about this? So isochron, equal age. Yeah?
So can you just go over again how age factors into the slope? Because I see that like it goes up with a higher portion of with a higher portion of the radius. How does age factor in?
Okay. What's going to happen is essentially, over time, on that isochron diagram, each individual point is going to evolve along a curved line like that. Okay? And where we are in the diagram right now reflects this iron meteorite evolving along a line that looks like that in this space. Okay, modern sediments have evolved along a line that looks like that, right? The Richardson meteorite, where'd my pointer go? Evolved along a line that looked like that. And so basically what I'm saying is that over time, as the radiogenic lead increased, its isotope ratios would have changed like that. So if we had caught this collection of samples like 1 billion years ago, they would not quite be there yet.